Okay, thank you very much. Okay, so I'm happy that we had several talks on neuroscience this time. It becomes a subject which is now in the field of mathematics. And what I would like to do here, just to give a few point of view on which have been used in this in mathematics, is the analysis of PDEs coming from neuroscience in the recent years. Of course, we had just a new talk by Douglas. But you know, mathematicians always work with problems which are 100 years old. So you have to wait a little bit before we work with what you said. So this comes back to not truly 500 years, but the 50s, so only 70 years ago. Hodgkin and Huxley explain what you explain us, by the way, that you can write the dynamics of an electric cell, especially neurons, but all electric cells, are driven by a system of equations, which is written here. This is the original Hodgkin-Huxley system. Douglas used more this formalism, which I call the Maurice-Lécart system, which is maybe more intuitive, where you have gating variables, ionic channels, synapses, which create a change of voltage, of the transmembrane voltage, according to reversal potential constants, which are known, and you have an input current. So this equation, despite all the defects they have and which have been described earlier, they have the same behavior, which means to create this firing, these spikes that contain certainly most of the information of the neurons. So when we hear the talk of Douglas, of course, the question of mathematician is what kind of mathematics? What can I prove on this kind of models? So here, for example, in this kind of models, the typical questions that the mathematicians have been asking are about slow-fast dynamics. So here you have a small parameter for some reason. The time scale here can be taken small, and the question is, how does this system behave? And this is one of the questions which has been interesting mathematicians. And it's not easy, even if now you want to explain that in a calculus course, it's not easy to show that when epsilon converges to 0, you get a solution. So we do that now. We have a neuroscience course in master where we explain that. And for example, that's also what was mentioned several times here. An example of this multi-time scale analysis is how you go from this picture where you have these spikes to this picture, which is what is intercurrent fire, where the dynamics which is slow here, you keep it. The dynamics here, which is complicated, you don't want to compute it, so you go back from this to this with a discontinuity. So this is an example of asymptotic problem where you say that the spike is very fast, and if it's very fast, you just ignore it, because you just know that it is there, and you go back. And this is an example of a slow-fast dynamics where you have done that. Okay, so it was mentioned also that these models are very complicated, very expensive to compute, and especially if you want to put all the complexity of a neuron as before. So you cannot use these models. You go to integrate and fire. And you hope that the only information is in the firing rate, and you keep it correctly when you do this asymptotic analysis or this network analysis that Francis Filbé showed. So at the opposite of the single network neural dynamics, you have global view of a brain. So this is, I would say, the maximum scale. And the goal now of teams of physicists, of biologists, or people doing imaging, would be to make a global picture of how the brain works. So they measure the complete connectivity of the brain, and they claim they have ways to do that. And then the idea would be, if you know the connectivity, you know this synaptic weight, this connectivity matrix, which relates a location X to a location Y of the brain, and you know what is the weight. And the Wilson-Cohen, there are many names for that. Wilson-Cohen, one of the names, give you how the activity, what is the activity, the number of spikes per unit of time, will evolve. So you have this equation where you have here the source term, the input, and the output is n of xt. So this is exactly also what I mentioned, what Doug mentioned. If you look at what is fashionable now, the deep neural networks, this is simply this kind of models with so sigma is a sigmoid, is a very stiff function. So they use this, and simply they put layers, because in our brain, especially in the visual cortex, you have many layers, and each layer sends information to the next one. So they use exactly that point of view to create these artificial networks. And then they compute the W by fitting completely with data that they have. So this is the origin of a deep neural network is here. It's 72. This model, which is here, and that many people use. So this model, it has been used very much. First of all, because it's a very generic model. When you think of any neural network, think of a social network, you can imagine it works in the same way. There is nothing which is physiologically related to neurons in this thing. So what kind of mathematics can you do on this? I think the most active field has been around bifurcation theory. And there are many people around that. And the reason of that is that despite the equation seems to be very simple, in fact, if you look, for example, even at steady states, you see that there's a huge family of steady states. And then to characterize them, you just follow by bifurcation theory, you follow these steady states. And you have also periodic solutions of that. So you don't need a source term, but even with a steady state without source, you find the periodic solutions. So this is so the mathematics about that is mostly a bifurcation theory, or of course existence theory also. These things are used also in when you want to understand the large-scale activity of the brain. For example, if you want to explain Parkinson's disease or associations that you observe in the brain for Parkinson's disease or for epilepsy, these models can. I mean, a system. By the way, you use a 2x2 system. You don't need the x variable to explain that. You just take two values and it's enough. There have been some very famous papers on explaining visual hallucination from this system. From the solution of this equation, you recover the image which is at the source term. So you can go back and say that the reason why this system have many solutions is also the reason that when you look at a picture, you can interpret it in different ways. And there is very specific in these questions of visual illusions, where you have pictures that you can see two ways, depending on the way you see it. You'll construct two images, and this is in the model. So this is, in some sense, the strength of the model. So these equations, I will not speak about that. I will try to explain other models and their properties, what they are doing, which are referring to small an homogeneous neural network. So don't want to explain the full picture. You want to explain at each location of this big network, you think at each location of 1 millimeter is itself a small homogeneous network, and this is what you want to do. So I will try to give an overview of all the models which are used. So as Zenan told us, if you want to depart from the integrate and fire model, so which means simply the ODE is that the DVDT is following a certain dynamics. Here I put just a relaxation. You have an input and a white noise. The integrate fire means that you don't describe the firing, the spike. When you reach a firing level, you go back to a reset, which is smaller than the firing. So this is a picture we showed later. This idea was introduced by Lapik at the beginning of the 20th century. And this allows a very simple description of neurons, much simpler than all these models that we have seen. So this is a picture I computed with this. So you follow the dynamics with an input current. When you reach a potential 1, you have a spike, which is not described. So this one is artificial. It's not in the model. I put it on artificially, and then you reset. You follow the dynamics. When you reach 1, you get another spike, and so on. So you can follow the spikes like that, and many physicists have been using that, including late David Xai, that was one of those who have been using this model a lot. And they have been compared to experiments. So in black, you have experiments. In blue, you have different models. So physicists are playing with this term to improve the model, to compare, to get the best fit with experiments. And they show that the best fit is not obtained like that. The best fit is obtained by putting inputs which are more like h of v equal exponential v or v squared, things which make that the dynamics would blow up. So there is a very fast scale where you reach a VF very, very, very quickly. So if you look at the stochastic differential equation, you can do it, perform Ito calculus and recover the Fokker-Planck equation, the Kolmogorov equation for the probability to find a neuron at a potential v, which is so the probability to find the capital V of t at the potential small v. And this gives you this equation that we have seen in the talk of Zenan, which tells you that you have the dynamics that we have seen here. You have the noise, and you write that's the firing of neurons. You write it that all the neurons which arrive at VF will fire at VR. Okay, so you have to take neurons at VF and put them at VR. So which means that there are no neurons at VF; they are automatically destroyed. And you have to compute how many neurons reach VF, and this is the number of neurons which reach VF. This is the flux. Okay, so this is the number capital N of t, and of course the capital N of t is also the capital N of tx of Wilson-Cohen. So the connection between the two is that if you want to see that, make a more refined model of Wilson-Cohen, this would be the small network which is at location x, and then you would make a big network out of that. And this N of t, if you compute it like that, when you integrate this equation because of Dirichlet, you get 0. This will give you N of t. Here you will get N of t also. So this is just the Lagrange multiplier to get a probability measure, or probability density at least. So we know that this linear equation has solutions. What we proved very early, it's that it has a solution, that there is a unique steady state of mass 1. This unique steady state is achieved with an exponential speed. So exponentially, this converges to the steady state, which is interpreted in terms of neurons as a total desynchronization. If neurons are not connected, they desynchronize. What is interesting is that, of course, the proof is relying on relative entropy. So this is a definition of relative entropy. You have two different reasons of dissipation. One is a noise. The other one are the jump from VF to VR. And when you want to prove exponential decay, the simplest is to get a Poincaré inequality or Hardy Poincaré inequality, which in this case means simply in the square case, so h is any convex function here. If you take the square, what you get and you put u equal n over p, what you can prove is that you can connect the entropy itself. You can control the entropy, the L2 norm, by H1 norm. So this is exactly the Poincaré inequality in the full space, which you know is not always true in the full space. It requires some properties on the steady state P of V, and especially in exponential decay, I mean in a Gaussian decay. Here you have an additional difficulty that you have a Dirichlet boundary condition, which means that P is 0 at 0. And to this Poincaré inequality, if in fact a result which is not very far, very old, it goes back to 2006. Or at least a variant of that goes back to 2006. And this one is not really in the paper, but the method of the paper gives you that automatically. Which means that these questions are using tools of functional analysis which are not so old. So now let's go to networks. So if you want to do networks, what you say is simply that the current that neurons receive through these synaptic connections is proportional to the activity of the network. So you have the activity capital N of T, which has been defined before, and you say create a drift is the voltage. So the current is proportional to the activity. So this would be the simplest model. Again, you can make things more complicated if you want, but this is the simplest possible model of that. And B can be positive, then you speak of excitatory neurons. Is B if negative, you speak of inhibitory neurons. And the noise, you can take it constant, even though it can be linear also in principle coming from the analysis. Again, this is on the half line V less than VF. You have a Dirichlet boundary condition. And this is the model. So, of course, you understand that N of T being positive, because the small n is itself positive, non-negative, you see that if B is positive, you increase the potential. So you go faster to VF, so you will fire faster. So you imagine that's really an excitatory. If B is negative, the drift drive you to the small value of B, which is inhibiting the signal. So all this model has been derived rigorously from systems of particles. So you take a system of n neurons. Each of them follow an integrated fire rule, so with this usual rule. And you simply say that whenever you have a spike, you create a small current, which I took here of this form. This is what is usually done by the group of people doing that. So you have this current, which is made of very, very small jumps, but very frequent. And you understand that if you make many, many, many small jumps very frequently, in the limit, you have a drift. You increase smoothly. That's what is proved by all this crowd of people, is that if capital N tends to infinity, a network like that will become independent, and the limit will be, the limit of these small jumps will be just a continuous drift. And the B here is connected to the beta here. And it's a big discussion around the scaling. Should you scale it like that, or are there other scalings possible? Physicists do not always agree with this scaling. So if you speak of this nonlinear problem, so this problem is becoming quite tricky, because you see that you have a quadratic nonlinearity in the drift, which is not very nice, because it reminds you of Clark conservation laws, shock waves, and so on. But this nonlinearity is driven by the boundary at VF. Not only is it driven by the boundary, but it's driven by the derivative of n at the boundary. So you get a tricky nonlinearity where the derivative generates the drift. So what is known so far is that there exist solutions. There is solution if B is not too big, if the solution is not too large, the initial data is not too large, or if B is negative. B not too big includes negative B, which is inhibitory network. So for inhibitory networks, you know that there are global solutions, and we know also they are globally bounded. Here, we know that there are global solutions, but we don't know if they are globally bounded. And if B is very small, near zero, we know by perturbation theory that it follows a linear equation. So you have exponential decay. So that's because when you have Poincare inequality, you have a term minus lambda u squared. You have always a place to put a nonlinearity, which will give you a term u cube in the analysis. So this is not really surprising. What is surprising is that we cannot prove, it's completely open to prove that in the inhibitory case, there is convergence to a steady state. So an inhibitory network should, like that with noise, should create a steady state. That's natural to believe it. It's completely open, and the reason it's completely open is that there is no principle like an entropy principle which would give you a hint of what is going on. So we know the steady state is unique in the inhibitory case. There's no doubt about that. But how can you prove that? It's an open question. And this problem is, by the way, connected to the Stefan problem. There are papers. There is a paper like that which uses this formalism to treat special cases of the integrated fire. So the way we prove that, one of the difficulties to prove that is the following. You do not have, because you have a drift which is nonlinear, you cannot have a comparison principle. You cannot compare two solutions. So you have to invent tools to compare super solution and sub-solutions to do that. So that's what we get as what I call a universal super solution, for example, is an object which is very simple like that, which is linear between VF and VR and constant afterwards, which grow exponentially. And this object has such a simple property that you can compare to any solution. And so there are objects like that you can use to control the solution. Especially you want to control the normal derivative here at the end. You want to control the derivative at VF. So here you know that if this is a super solution, you also control the capital N, which is derivative here. And then you have regularizing effect and Poincare inequality to help you. This shows these movies that you have seen in the talk of Zenan, by the way, in a much better way. He has done a much better calculation than that. But this is an illustration of the fact that you converge to a steady state when you have an inhibitory network. So you have here the kink because of the right-hand side, the Dirac mass, the jump on the derivative. But whenever you compute the inhibitory network, that will be what you get. So it's not a proof that, that it works, but it's an indication that it should work. And this is the activity. So the activity is becoming very quickly constant. So that's what is predicted by the theory. What we know is that if you are not in the conditions of existence, you have blow-up, which means that for an excitatory network, if the initial data is concentrated nearby VF, or if B is large enough and you give me the initial data, so in the large, there will be blow-up. And this is one of these cases of a very surprising effect, that blow-up is related to the noise. When you increase the noise, you will converge faster to the blow-up. So it's one of these cases of Turing instability where the noise doesn't help for regularizing, it helps to create and this is very intuitive, by the way. There is a very simple explanation. I mean, if you think of the dynamics v dot equal minus v, of course the dynamics, and here you have Vf. Of course the dynamics, and you have time. So the dynamics of v dot equal minus v is decreasing. So the determinist dynamics will never blow up. If now I add w dot from here, maybe I will decrease, but sometime I will have jumps. Okay? So that's really the noise which creates the activity. And that's the reason why the noise creates this blow-up, because this activity will be enhanced by the drift, and then you create the blow-up. So this is what is surprising. So in fact, this blow-up is not really, we don't really know very well. There are works now explaining that you can continue solutions after blow-up. So blow-up is not really a blow-up. It's simply the symptom of synchronization of the network. So when you reach this blow-up time, it means simply that a number of neurons are firing together. Okay, this was very clear in the movies. I should have taken the movies of Zenan. They were very good on that. So you see it very clearly. And this is what you observe. So this is the same movie in the excitatory case. So now you create the kink, as usual. You create the activity, but you don't stop the activity. So you see that the slope here, which is the activity, increasing, and you see that the boundary condition here cannot be sustained. So it loses, this means that you lose the boundary condition, the Dirichlet boundary condition, which means a number of neurons, proportion of the system will blow up. Will arrive at the same place, so this is the reason it stops. Okay, let me go quickly to the next step. So you can fix this problem in different ways. So one way, I think this is what Zenan has been explaining. One way to do it is to say that the firing rate, the firing potential is not fixed. It is random. And then you extend the problem. That's blow up. That means that n of t tends to infinity when t tends to t star. That's what you see, that the slope, you have a slope like that, or you have your kink here, and your slope becomes infinite. But it becomes infinite in such a way that the solution itself, so n of t, Vf, goes to something positive. Okay? So you lose the boundary condition. Because of these big derivatives, you lose the boundary condition. Is Dirichlet, but you cannot continue. You cannot sustain the boundary condition. That's surprising because it's just drift and diffusion, but it's like that. Because the drift is related to the derivative at zero. So it's at zero. So, okay? And what we know is that n of t is not integrable on 0 t star. So which means that it blows up in such a way that it becomes a singular measure, the Dirac mass, which is related suddenly to this jump. So one way to get rid of this is to extend outside in the full line. And so you do that by extending, by saying that your Vf is random, You can also put a refractory state. Okay, the refractory state doesn't also blow up. So, so if you put a refractory state in, it's not enough. A refractory state where after firing, neurons stay in a refractory state for some time. This will not be enough to have a global solutions. So you need more. And more is to, for example, to extend like that to a full line. And if you do that, now you compute and you get periodic solutions, as you see now. Because now, as you see, the solution is going beyond 1, because the VF is no longer fixed. You still want to have a stiff derivative, so you create first the kink. You want to have a big derivative, so you get a big. You create big derivatives, but it doesn't. The solution doesn't blow up. So it, in some sense, when you reach this blow up time, you send a part of the network back to VR, because you reach VF very quickly. So you go back to VR, and then you can continue the solutions, and you get periodic solutions. So this is the reason why this system is a reasonable system for a network. A network should generate periodic solutions because your brain at rest generates periodic waves, which are many of them, which are well recorded by ECG. So very quickly, let me now go. So okay, of course you understand there are many questions we do not understand about that. Problem, but now you can go further. You can also consider models that I think were developed by David Xay and Mike Shelley at the origin, and McLaughlin, the group that was mentioned by Douglas. If you do that, if you go to the Maurice-Lécart system, now you can get also an integrated fire model for that. And the integrated fire model will say that you have a potential, you have gating variables. Your potential evolves according to the opening of the gating variable. Here there is only one gating variable, and this gating variable is driven by the activity of the network. So this is the simplest model you can imagine with these ionic channels. And what you think is that the noise is on the opening and closing of the ionic channel. So the noise now comes in this variable. And the G wants to go to rest, to an equilibrium, which is driven by the activity. And the activity is not written here, but it's, again, the number of potential of neurons which reach the potential VF. So this depends on G, but there is a mistake. N of T now depends on G because you look at the number of neurons in V which arrive at potential VF, and this creates an activity at the gating level G. So in some sense, you can see that as a Vlasov equation or a Fokker-Planck equation, just comparable to a macroscopic state, which is the integrated fire. Here you have a microscopic state, integrated fire model. So we don't know so many things about that, by the way. So what we know is that there are steady states. So there are global equilibrium. So if you can compare to all the methods, when you want to look at the kinetic equation with the kinetic Fokker-Planck equations, you have 20 methods to prove that you converge to equilibrium exponentially fast. Okay, none of them you can apply to that. The only thing we know is that the steady state, the Maxwellian, if you want, is in this stupid space. It's better than L1, not so much better, but it's more than L1. And we know that there are global solutions to that which are bounded in LP and which do not blow up, by the way. We don't know, this is certainly not the best regularity for the steady state. We don't know again if these converge in large time to something. mostly everything is open. What we did is put epsilons, fast scales, for example, indicating variable to recover a macroscopic variable that you can do. So we're, again, cheating a little bit on the assumptions, so we have assumptions which are too strong on that. So capital N of t is capital N of t on G, and it is the number of neurons, the flux of neurons arriving at VF. So this, you take this at VF, and this is N of t of G. Okay, this is the flux of neurons which are at VF that you will put at VR. But VR equal 0 here. Yes. You always have a relative entropy estimate. Any equation which satisfies which comes from probability, which have preserved positivity, have always a relative entropy. Okay. So the only question is there a steady state which is smooth enough to do it? So that's also what Marie explained. You have always a relative entropy. Okay, so this is the second type of equation. Now there is another class of equation which is also interesting in neuroscience for describing assemblies of neurons, which are completely different, which are the following. So now what you say is, in fact, it's exactly the contrary of what you explained earlier. Some people say, okay, voltage, we completely ignore it. It's too complicated, too much information. I cannot make a neuron network with this. The only thing I'm interested in the time between the spikes, because we think that all the coding information in the brain is the distribution of spikes. So you make a model in which n, the distribution, is the number of neurons which is firing after since the time s. So s is the time after the last discharge. Okay? So you discharge, you put the time scale s at 0, then you wait, and when you discharge, you put it again at 0. So how do you describe that? The time s, of course, evolves with the chronological time t. You have here a rate of firing which depends on the activity of the network, which is capital N, which is always the same thing. And you describe the neuron at time s equals 0 as all those which has been firing at time t. So you integrate this to get the activity N of t. And this activity creates an acceleration, if you want, of the firing rate. Okay? So this one, you don't see the potential, just see the distribution of neuron in the time, according to their time after spiking. So this theorem is the same if B is small or large, or if you are in a linear case, you converge to a steady state. You have an entropy, or you have also a relative entropy, which helps you to do that. You have some kind of okay. You have many ways to analyze that. One is Poincare inequality. The other are method of semigroups by Michler and Mouot and their collaborators. So the main difference between integrate and fire and this one is that in the integrate and fire, when the connectivity is large, you always blow up. In this one, if the connectivity is small, you don't blow up. If the connectivity is large, you do not blow up. You do not have synchronization or blow up. You have synchronization only if B in a certain middle range. So that's different. So large B, in some sense, everybody is connected to everybody too strongly, then all the information is shared and it's like becomes really homogeneous, and you don't have a synchronization. If you are in the middle range, what you observe are these solutions. With also this capital N of t, and the difference here that we observe many types of with the same parameters, many types of periodic solutions. So this periodic solution here on these ones with two spikes are with the same range of parameters. So for those who think that PDEs of first order, or especially this stupid PDE dtn plus dn dt plus dn ds is too simple, which intuitively is, this is the solution n of st of this PDE. So this is what you observe. So it seems to be simple. It's simple to write. Solutions are not so simple. But they become periodic. So again, you have synchronization. You are in the middle range of B. You have synchronization. It becomes periodic. And you get this. So Delphine Salor was able to compute analytically solutions which are periodic for this equation. In some special case, of course, you fix the rate R in such a way that you can compute analytical solutions. So we know by using integrate and fire, it's completely open to know whether there are periodic solutions or not. We don't know. There is even not a bifurcation theory which has been written because you have Dirac masses and jumps everywhere. Here you can have analytical solutions. So at least we know examples where you have solutions. I will stop here, but just a remark which I find very surprising, which goes back to two persons, which is Dumont and Henry. Maybe someone knows about that, but I'm really surprised by this result. So it's a linear equation. So what the theorem tells you is that if you take the H structure equation, okay, so a linear case, if you compute this kind of Fourier transform where Q is a specific, so you integrate in the variable S the function S, you get a new, some kind of Fourier transform, and this Fourier transform satisfies the Fokker-Planck equation. Okay? Very surprising. Okay, so you agree that if you take the heat equation dtn minus Laplace n equals 0, n of tx equals 0, if I compute n hat of t xi equal q of x and xi n of tx dx, you get dt n hat plus xi squared n hat equals 0. So you can transform a PDE in a linear equation. You can also transform a first-order equation in a Fokker-Planck equation. I don't know which equation you can transform in another equation by such a transform, but this one you can do. And the way back is not, I don't know. So they have a theory which is not so nice to go back. So which equation can you transform in another by this kind of transform is an open question, which I like. Okay, I will stop here just to tell you also that what you can do. Okay, when you have that, you can do learning in a funny way, which you can say that, okay, this synaptic weights B, I call it W. You can also think that the network, different networks with different values of B or W now, will handle the information differently. And you can say that now a real network is a network which manipulates all the information independently with the variable W. And you would like to know if you have an input, which is treated also differently depending on the value of W, what will be the output N of W. And this depends on the connectivity of the network. So you can learn the connectivity of the network by your rule, which you put here by some kind of learning rule. And so you can make a learning theory in the phase space where you learn what is the best distribution of weights, if you want, according to the signal. So I will not do that. And though, again, you can ask many questions around that. An example is that you have a signal like that, an input like that. You can learn a connectivity which is like that, and the output will be something like that. These are artificial oscillation to the numerical method. And if you put another output, double Gaussian, another input, the output will be different. So you can distinguish different incoming signals from the outgoing signal. This is the contrary. If you put as an incoming signal the double Gaussian, you get an output which is more or less the same as before. You will get a connectivity which is different. But now if I give you this output, this input, which is a Gaussian, I get a signal which is completely different. Okay, so like that, depending, you can learn the signal and then distinguish if you hear the same music or not. So this is what you can do with this kind of networks. Okay, so I stop here. I thank my collaborators on this, which are here, and I thank you very much for your attention. Ah, okay, yes, you could make, yes, that's a good observation, yes. Yeah, it would be interesting to write and to create all the superposition. Yeah.
For the linear case, it's still hard, so there's nothing I can
yeah.
I have another question. So for the conductance voltage model.
Yes.
So even if you can do the rough entropy estimate, so I think you are still running into trouble of like hypercoercivity, right? You only have the diffusion in the G direction. You have no.
Yes, absolutely. The question is how you handle the derivative in V because you have no diffusion. So you get an. Yeah, that's the reason it's not so easy to compute, even to prove that the Maxwellian is smooth. We don't know how to prove it. I see. That's the reason. Yes, it's hypercoercive. Apocoercive. Yeah.
Yes, so maybe the Unalov will not be exponential, right?
Nobody knows. If you find a method which works, it would be. So we don't know. The problem is that you don't know even what is a Maxwellian. You don't have a formula for Maxwellian. Yes. And the Maxwellian depends on V and G. It's not like in the usual Fokker-Planck where it depends only on V. So it depends here on V and G. So whatever the manipulation you want to do, you are blocked at some point. Yes, because what you want to see is really the synchronization of the network. We want to see the activity of the network. That's what is of interest in practice. That's what you want to see, yes.
And has it determined to extend this solution, there must be some quick sense or something more generalized than
Okay. The only paper I know on that is a recent paper, I'm not sure even if it's published, by a group of people in Nice, Delarue and his co-authors, where they have a probabilistic view, and in some sense they have they reset, after blow-up, they reset the solution to a new one. I really cannot understand analytically why they do that, but there are formulas which explain that you have to do it that way. And I cannot really understand.
So there is no knowledge available on properties of these extensions?
No, but the conjecture would be that there is a unique natural way to continue. Whatever you do, there should be a unique way to do it because these formulas are extremely robust in terms of probability. So it would be, and because you asked a question also, there is something which is interesting, is of course the integrated fire model is very connected to chemotaxis. Just an observation. Yeah, absolutely.